Here is this formula is used a lot in AP Physics questions that I have seen related to the waves. So I wanted to go over this concept and explain to you how this formula can be used and how to solve questions related to this formula. Before this video, you probably want to watch simple harmonic motion video and wave and harmonics video that I posted. I'm gonna attach the link to this video as well. So the speed of waves in a stretched string depends on the tension F in the string as well as the mass per unit length. So sometimes they use mu as mass per mass. So you see it right here. It is mass per unit length. How much mass per length? It's almost like density of the string. And the string as explained below the question, and they give you the formula. So in this formula, you have the velocity of the string is going to depend on T, which is the tension, and on the mass and the mass per length of that string. Here's one of the examples that I wanted to look at. And I think the formula is going to be used in this question. So a string of length 3.2 meters is connected to at one end of the mechanical oscillator with a vibrative frequency. So there's oscillator and it has a vibration. So here's oscillator and it has a vibration. The other end runs over a pulley to the mass M. So here's the mass M that hangs vertically. When the oscillator frequency is set up to 200 Hertz, so this one is 200 Hertz, the standing wave in the diagram is set up on a string. So they show you the standing wave in the diagram. So what I'm going to look at, the length of the string is 3.2 meters. So 3.2 meters. That means that's my L, 3.2 meters. But I see there's one wave and a half. So L is equal to 3/2 of the wavelength. And L is 3.2 equals to 3/2 of the wavelength. So the wavelength is equal to 3.2 times 2 over 3. So the wavelength is equal to 6.4 divided by 3 and gives me 2.13 meters. So that is my wavelength. For B part, they ask, what is the wave speed in the string? So I have the wavelength and I have the frequency. So the wavelength is equal to 2.13 meters and the frequency is equal to 200 Hertz. So I can find the velocity of the wave, which is 2.13 times 200, which gives me 426 meters per second. What is the lowest frequency of the oscillator that will produce a standing wave of the same speed? So the speed, we're going to use the same, 426. And what is the lowest frequency? So they're changing the frequency of the oscillator, and they want to produce the lowest frequency needed to produce a standing wave. So if the length of the string is 3.2 meters, so I can produce first harmonic. So first harmonic is going to be this much, and this is only 1/2 of the wavelength. So your L in this case is equal to 1/2 of the wavelength. That means your wavelength actually for the first harmonic would be 2 times 3.2, which is 6.4 meters. The speed is given and the wavelength is given. I'm looking for the frequency. The velocity is equal to lambda times the frequency. So the frequency needed is velocity, 6.4, It is 426 divided by wavelength, which is 6.4. And that is 66.7 hertz. For D part, assuming the speed of sound in air is 343 meters per second, what is the frequency of the sound wave created by the string when vibrating as shown in the diagram? So in this case, I have velocity is given 343, and the wavelength I found is this much. So that's lambda times the frequency. Lambda is 213, as shown in the diagram. And they ask you the frequency. So the frequency for such the standing wave would be needed as 343 divided by 213, and gives me 160 hertz. Here's another question that I have seen on AP exam, one of the multiple choice questions probably. An open pipe of 25 centimeters long produces a second harmonic standing wave at 30 degrees Celsius. Determine the frequency of the sound in hertz. If they give you degrees Celsius, that's most likely they want you to use it to find the actual velocity of the wave at certain conditions. And the velocity of the wave depends on the temperature. So the hotter the temperature is, the faster the wave is going to travel, because the molecules in the air are already excited, and so they will be easier to transfer the energy. So if you plug in this into the formula, you have 331.4 plus 0.6 times 30. So the velocity of the sound under these conditions is 349.4 meters per second. So I'm going to use this velocity for my calculations. And they say an open pipe is second harmonic, right? So the pipe is 0.25 meters. So it is 0.25 meters. And produces second harmonic. When they say an open pipe, it means open on both sides. So that means you have, this would be, I'm going to do in green, first harmonic. So this would be the first harmonic, and this would be the reflection. And you need the second harmonic. So the second harmonic is going to look like this. And this would be the reflection of the second harmonic. And from here, you can see it goes from crest to crest. So your wavelength in this case is equal to L, and equals to 0.25 meters. Determine the frequency. So I know the velocity and I know the wavelength. The frequency is equal to the velocity over the wavelength. Velocity is 349.4 divided by 0.25, and I guess that will be equal to 1398 hertz. Next question I have for you is another AP physics question that I found for you in one of the books, or not FRQs, but multiple choice questions. The speed of sound wave in the air is 340. So usually when they don't give you the speed of sound, you assume it is 340 meters per second. Determine the fundamental frequency, that means the first harmonic, of a closed and air column. Closed and means you have pipe that is closed on both sides, that has the length. So the length of it is 67.5 66.5 centimeters, and an open end. So both sides open, both sides closed. So both sides open, and both ends. And oh, this one is closed and air. So on one side it's closed, the other side is open. So one side is open, the other one is closed, and the other one is open on both sides. And the length is still the same for both, 67.5 centimeters. And I need to determine the fundamental frequency. So fundamental frequency for the first one is going to be this one. And again, I suggest you to watch the video that I post in the link if you don't understand why I'm drawing it this way. And open on both sides is going to be fundamental, this one. To produce the full wavelength, I would have to have like this. And so when it's closed on one, let me redraw it this way. When it's closed on one end, I have 1, 2, 3, 4 parts of one wavelength from the crest to the crest. What I see in my first picture right here is only 1/4 of it. And again, in the lessons I explained to you, you don't have to memorize, it's easier to derive than memorize. So what you see here, L, is equal to only 1/4 of the wavelength. So from here you can figure out what the wavelength is equal to. From here the wavelength is equal to 4 times L, which is 4 times 0.675 if we do it in meters, and the wavelength is equal to 2.7 meters. And I need to find the frequency. So the frequency is equal to the velocity over the wavelength. That is 340 divided by 2.7. So the frequency is equal to 126 hertz. For the second part, if we look at the wave that is here, it is missing this part to make the full wavelength. So I have it like this, to go from the trough to trough, trough to trough. So if I look here, I have, I should do it like this so it doesn't look a little bit too long. So every wave has 4 parts. So I have 1 part, 2 parts, 3 parts, 4 parts. So in my case, I already have this part. So I already have 1/2 of the wavelength. So in this case, I have L is equal to 1/2 of the wavelength. That means I can find my wavelength is equal to 2 times L, which is 0.675, and that is equal to 1.35 meters. And then from here I can also find the frequency, which is the velocity over the wavelength, 340 divided by 135. So it is equal to 252 hertz. For next question, I have a sound wave resonates in an open tube with 2 open ends. What are the wavelengths of the 3 lowest resonating frequencies generated in the tube? So I have a pipe open on both sides. So open both sides pipe. And 3 lowest frequencies. So the first frequency is going to be the fundamental one. The next frequency is this one, second harmonic. And the third frequency is this. And this is the L. In the first one, I have the L is equal to 1/2 of the wavelength. In the second one, I have L is equal to lambda. And in the third one, and I need the first three, right? The lowest frequencies. And the third one is equal to 3/2 of the wavelength. So the wavelength in this case is equal to 2 times L. This case it is equal to L. And in this case it is equal to 2/3 L. Do you see why it is B? So the answer shows it is B. So that would what you would need to show if you had this question on maybe part of the AP exam question. Here's another question. The lowest frequency in an open tube is 300 hertz. So they give you the lowest frequency, the fundamental. It's an open tube, right? So I have open on both sides. And the lowest frequency, it's fundamental frequency. You have L, and you have L is equal to 1/2 lambda. And the frequency is, in this case, they give you is 300 hertz. What are the three following frequencies will resonate in the tube? So let's look at the other one and the relationship between. So I know the velocity is equal to, they talk about the frequencies. The frequency is equal to velocity over the wavelength. So for the next one, next three, right? Yeah, 3 lowest. So the next 3. So for the next one again, I'm gonna have this one, and the next one is this one. Here I have lambda, and here I have 3/2 lambda. The frequency here is equal to, and the velocity is the same for every single one of them. So I'm going to rewrite this here. And I'm going to say the frequency is equal to 300 hertz. But it also equals to velocity over lambda, and lambda is 2L. In this case, the next one, it's also velocity, but your lambda is L. So that means my frequency is twice as much as the previous one, because the other one was divided by 2L. So this one is going to be 600 hertz. And the next one is equal to velocity over L, but L is lambda, and lambda is equal to 2L over 3. That means this frequency is 3 times as big as the initial one. So the last one is 3 times is 900 hertz. And the answer is A. You have, wait, let me see. Oh, the next 3. I found the first, second, and third, and then you need the next 3. So you need one more. So it's open on both sides. Here is the next one, and L is equal to 2 lambda. So the frequency is equal to the velocity divided by 1/2 of L. And that means it's twice, it's twice lambda over L, or it's 4 times V over 2L. Oops. Not enough space here. Let me do this way. Over 2L. So that means it's 4 times 300 hertz, which is 1200. So that's why your answer is A, because they ask you to find what are the 3 following not the 3 lowest, but 3 following. So not only the 3 lowest, they give you the first one, they ask you the 3 following to find. Here's the next question. The lowest frequency in an open pipe is 200 Hertz. Which of the following frequencies will resonate in the tube? So let me look at it this way. It is open tube, so that means open on both sides. So I have 1. I'm going to look at the relation 2, 3, and 4. And this is your L. So in this case, L is equal to 1/2 lambda on both sides open, right? 1/2 lambda. In this case, L is equal to 2/2 lambda. And the next one is going to be 3/2 lambda. And the next one is going to be 4/2 lambda. And the frequency is equal to, let's write the lambdas first. The wavelength is equal to 2L in this case. The lambda is equal to 2/2L in this case. The lambda is equal to 2/3L in this case. And the lambda is equal to 2/4 L in this case. And velocity in the first one is equal to, the frequency, they ask about the frequency. So the frequency in this case is equal to velocity, and velocity only depends on the medium in which it travels. So if the medium doesn't change, the velocity is going to stay the same, and frequency only depends on the source. So the source produces a certain frequency, and then it travels through a certain medium. When the medium changes, velocity changes, but the frequency stays attached to the source. So that is equal to 2L. In this case, frequency is equal to over 2L, and 2 appears here because it's 2L divided by 2. In this case, I have V divided by 2L over 3, so 3 appears here. And the next case, I have velocity divided by 2L, but then it's divided by 4, so 4 appears here. So it looks like if this is my fundamental velocity, the next one is twice this much, and the next one is 3 times this much, and the next one is 4 times this much. So if they tell you that the lowest frequency in an open pipe is 200 Hertz, which one of the following could be the answer? So it would be 2 times 200, 3 times 200, 4 times 200. And the only one that is number, or digital number, times, or integer number, times the 200 is D, 400. This is another question from the AP exam that I have seen. A spring of constant K, hangs at its natural length from a fixed stand of mass 3 kilogram, and I'll let you read the question, and then I don't want to take too much time. I want to fit it within 30 minutes. I'm going to let you read the question, pause it, and then I'm going to start working on the question. So for the first part, for A, they ask you to find the value of quantity X, the extension, by how much the mass is going to stretch the spring. So I have, because it is in equilibrium, so you have 2 forces acting on the mass. It's mg and the force of friction. So the force of friction is equal to mg. That means kx is equal to mg. K is given 100, x we need to find, and mg mass is given 3, so that is 30. So ux is equal to 0.3 meters. For the next part, they say the string is pulled down additional distance x and released. What is the potential energy of the spring at this distance? So the potential energy of the spring is 1/2 kx squared, and that is 1/2 k and x squared, which is 0.3 squared. And the answer is 4.5 joules. The next one is going to be, what is the velocity, maximum velocity of the mass when it passes through its equilibrium? So its equilibrium, so the mass is pulled down certain distance x additional, and then it comes back. It will have zero velocity at this position and maximum velocity at this position, zero velocity back here, and then it will just jump there and back. So the potential energy of the spring is going to be converted into the kinetic energy of the block. So I have 1/2 kx squared is equal to 1/2 mv squared, and I'm looking for the velocity. 1/2 and 1/2 can be cancelled, so the velocity is equal to x, the square root of k over m. If I plug in my numbers, I have x is 0.3, k is 100, and m is 3. So does that look like 1.7 meters per second? For the next part, they ask you how high above the equilibrium will the mass be transferred, and because it's potential energy goes to the kinetic energy and goes back to the potential energy, so x is also going to be 0.3 meters. And then what is the period of the oscillation of this mass? And to find the period, I have t is equal to 2 pi, and the square root of, this is the spring, so it is m over k. So now if I plug in my numbers, I have 2 pi and the square root of m, which is 3, and k is 100. Does that give us 1.1 seconds?